Hi, my name is Bill Kinney, and this is my second video to help people study for the AP Calculus AB exam. In my first video, which I'll put a link to, I did Section 1, Part A, which is a multiple choice, no calculator portion. I'm going to continue with a no calculator portion on this video. We're doing Section 2, Part B, no calculator, but this is free response. So you're graded not just on the answer, but also your work. Okay, so you need to show your work. And you also need to give explanation where requested. Whenever it says justify, like right there, you need to give explanation, and it's got to be a good explanation as well. So this is harder. On the actual AP exam, when you do this part, you're going to have an hour to do 4 problems, so you need to average 15 minutes per problem or less. I want to give you more variety, so I'm going to do 6 problems, which then you would want to try to finish in an hour and a half if you're following along with me, and I would recommend doing that, pausing the video, and doing the problem on your own, and then coming back and seeing what I do. With this problem, the full thing is not shown because you need to see the graph as well. You can pause it there if you like. It's a little tricky. We got some intercepts that are occurring, for example, at half units, like this is at 1.5 and this is at 4.5. It's a pretty challenging exam, like I said. You have to read carefully, and again, you need to show your work and give explanation where required. Let's start this first problem. Let f be a function defined in a closed interval from -6 to 6 with f of 0 equal to 2. Really, really important to keep track of details like that. What you see down here, partially, is the graph of f prime, the derivative of f, not f itself. That's really key to getting this problem right, okay? That's the graph of f prime. And by the way, I don't have any physics, velocity, position problems on this sample exam, but this very well could be a similar kind of problem that you would get in physics, where this would be the graph of the velocity, okay? And you'd be trying to figure out things about the position of the object. But we are not dealing with the application in this particular setting here. Again, that's the graph of f prime. In part A, we need to find f of 4. We can't just use that graph's values, okay? That's the graph of f prime. If you think about that for a second, I hope it comes to your mind that we need the fundamental theorem of calculus to find f of 4. Fundamental theorem of calculus relates changes in a function values to integrals of its derivative, integrals of its rate of change. Part B, we want to find all values of f at which the graph of f has a point of inflection, where the graph changes concavity, from concave up to concave down, from a smile to a frown, or vice versa, concave down to concave up. They could also look like this. Could be decreasing the whole way. It would be changing concavity right about at that point from a smile or a partial smile to a partial frown. More importantly, the slope, the derivative, is changing from increasing through negative values towards 0 to decreasing. The other kind of picture you could have would look like this. There the derivative is always positive, but it is changing from decreasing to increasing. So we have a change in concavity from concave down to concave up. At this point, that would also be an inflection point. Part C, on what intervals is the graph both decreasing and concave up? So the graph is going down, but concave up like that. And finally, in part D, we've got a second function g, defined by this equation. It's quadratic. And a third function h, defined, well, you can't quite see it here because the pen is being lifted up. There it is. That's a composite, f of g of x. We want to find h prime of 3. Find h prime of 3. Think about that for a second. I hope you remember you're going to need the chain rule to take the derivative of a composite function. All right, let's go ahead and erase these lines again and work on the problem now. Need to move it up so we can see the graph. Here we go. Part A, again, find f of 4. It's not the value of this graph at 4, but we do need to use that graph. The fundamental theorem of calculus, which we usually use to evaluate definite intervals, here we're sort of switching it around. We're using it to find the change in a function. F of 4 minus f of 0 is the integral over that interval from 0 to 4 of the rate of change of the derivative, whose graph we are given. Now, you definitely do not want to take the time to try to find a piecewise formula for f prime. Instead, use the fact that it's piecewise linear to help you do this integral by thinking about it in terms of areas. That's really key. So again, the interval is from 0 to 4. Careful here, I purposely made it 4 instead of 4.5. That's a little tricky here. I purposely made it a little tricky. Also, this is an intercept of 1.5. You can take the time to double check that if you want. This area, under the graph when it's above the axis, area of a triangle, contributes positively to the integral. Whatever this area is, it's at 1/2 base times height, that's going to contribute positively to the integral. But this area down there, because the graph is below the axis, contributes negatively to the integral. It's probably best to split this area up into a triangle over here and a trapezoid over here. You could split that trapezoid up further into, say, a square up here and a triangle down there. But there's also a formula for the area of a trapezoid like this, which is the base up at the top, which is 1 here, times the average of the two heights. And again, these areas contribute negatively to the integral. But again, also keep in mind that the integral is not the final answer, because we need to use the fact that f of 0 is 2. After we do the integral, we're going to have to add 2 to both sides to get the final answer. So what will the integral be? What's the area again of this triangle? 1/2 base times height. 1/2 or 0.5 times 1 is the base right there, times the height is 1.5. That's going to be 0.75 or 3/4 if you prefer. It's fine if you work with decimals or fractions here. In general, you may want to work with fractions because you are not allowed to use a calculator, but these decimals are going to be simple enough that we can work with the decimals. That contributes positively to the integral, plus 0.75. The other two areas contribute negatively. I'm going to subtract the areas. This triangle right here has a base of 2 and a height of 3. 1/2 base times height. 1/2 times 2 times 3 is 3. It contributes negatively to the integral, so I'd subtract 3 because the graph is below the axis. I'm also going to subtract the area of this trapezoid. Again, its base is 1. Its two heights are 3 and 1. The average of 3 and 1 is 2. 3 plus 1 over 2 is 4 over 2 is 2. Base times the average of the heights is 1 times 2 is 2. We subtract that as well. So this is 0.75 minus 5. That's going to be negative 4.25. But now don't forget to add 2 to both sides. The final answer for f of 4 is going to be negative 2.25. As a fraction, that's negative 9/4. Okay? That would be the final answer for part A. This is the kind of work you want to show. On to part B. At what values of f does the graph of x find all values of f? Actually, there's a typo here. This should be an x here. At which the graph of f has a point of inflection. And justify. Okay? It says justify. Make sure you give brief but valid reasons. What kind of reason can we give here? What are we looking for? When do you have a point of inflection? Point of inflection, again, is when you change your concavity. Concave up to concave down like this, or like this. Or it could be like this, right there, or it could be like this, right here. Any way you slice it, the sign of the second derivative is changing. With regard to the first derivative, it's changing from increasing to decreasing, or vice versa. Here the derivative, the slope, is increasing when it's concave up. Then as you pass through the point of inflection, the derivative, the slope, becomes decreasing. Here it's decreasing, then increasing. Here, careful, this is actually an increasing slope. It's getting closer to 0 here, and then it becomes decreasing. Here it's a decreasing slope, and then it becomes increasing. So whenever it changes concavity, the second derivative changes sign, the derivative changes from increasing to decreasing. That's going to occur at x equals negative 3. The derivative is changing from decreasing to increasing. At x equals -1, the derivative is changing from increasing to decreasing. And at x equals +3, your derivative is changing from decreasing to increasing. So as far as writing an explanation, you could say something like this. Inflection points, I will abbreviate, you may not want to abbreviate on the exam, occur when f prime changes, careful, not from positive to negative or negative to positive, from increasing to decreasing or vice versa. You could also say the second derivative changes sign. Either reason is valid. So the answers are x equals -3, -1, and +3. Okay? That's the kind of reasoning you could give. Now, technically, the second derivative does not exist where the first derivative has a corner, like at these points actually, -3, -1, and +3. There's corners at those points, so the second derivative, which is the derivative of the derivative, actually does not exist there, but it does still change sign from negative to positive to negative to positive, the second derivative. On to part C. On what intervals is the graph of f both decreasing and concave up? Intervals in the graph of f, the original function, which we do not see, decreasing and concave up. In other words, the graph looks like this. The graph looks like that, the derivative must be negative. The slope is negative. But as concave up, the slope is increasing. A large negative value far away from 0 to a small negative value close to 0. So we're looking for where the derivative, f prime, is both negative and increasing. Negative and increasing, like right there and right there. When x is between -3 and -2.5, yes, that's what that is there. And when x is between 3 and 4.5 is right there. Okay? And doesn't say to justify, but you could certainly give a brief reason. You could say, I'm looking for where f prime is negative and f prime is increasing. You could also say f double prime is positive. Should you write your answer as open interval or closed interval? I think it really doesn't matter. Technically speaking, you could say the closed intervals. You could say the closed interval from -3 to -2.5 and or union with the interval from 3 to 4.5. I'm doing closed intervals, but open intervals should be all right as well. You could also use inequalities like this. Technically speaking, it should be true actually on the whole interval here. So that's the answer to part C. Part D. Let a second function be defined by this equation. Again, that's quadratic. And a third function, h, be defined by that equation. Find h prime of 3. That's a chain row problem because that's a composite function. H prime of any number x is the derivative of the outside, f prime. Plug in the inside function g of x, evaluated at x times g prime of x. But I can go ahead and plug in 3 from the start. Take the derivative of the outside function, f. Plug in the inside function evaluated at the input, 3. Multiply times the derivative of the inside function at that value of x, which is 3 here. All right, so we just need to evaluate these things. G of 3, looking at the formula for g, is going to be 3 squared minus 2 times 3. That's 9 minus 6 is 3. Double check that. Hopefully I don't make a mistake here. G prime of x is going to be 2x minus 2, so G prime of 3 is going to be 6 minus 2 is 4. We're also plugging g of 3, which is 3, into f prime. What is f prime of 3? I need to look at the graph. It's a little tricky here. You might be saying, oh, I need the derivative of this at 3, which is undefined. You might say the answer is undefined, but that would actually be wrong. This is the graph of f prime itself. I'm not after the slope of this graph, which again doesn't exist at that point. I'm after its value there. F prime of 3 is negative 3, the second coordinate of that point right there. Okay, so it's tricky. There's lots of little tricky things to be paying attention to and to be looking for. So the final answer can be found by plugging these things in here. F prime of g of 3 is f prime of 3 because g of 3 is 3, which is negative 3. That's the negative 3 first. Times g prime of 3, which is 4. The answer is negative 12 for part D. All right, on to the second question. So again, when you actually take the exam, you'll have 15 minutes for each of these problems. You'll have 4 of these problems total for a 1 hour part to this exam. But again, I want to show you more variety, so I'm doing more problems. I'm doing 6 problems total. The second problem, as you can see, as you glance through, it looks like an optimization problem over a closed interval. Okay, not over all of x, over a closed interval. You should make sure you remember right away what you want to do to find the absolute max and absolute min, sometimes called global max or global min, is find the critical points. Compare the value of the function at the critical points and at the endpoints. You do not need to use the first or second derivative tests. Those are for local maxes and mins. I mean, you could if you wanted to, but it's not necessary. All you need to do is check function values to find the absolute max and absolute min, showing your reasoning, meaning essentially showing your work. You could add some writing. You could say, I know the max and mins will exist, absolute max and mins, because the function is continuous. You could say something like that. That's called the extreme value theorem. And you could say, I know they either occur at the critical points inside the interior of the interval or at the endpoints of the interval, and so I need to check them. I'll just show the math itself. Take the derivative of x minus 2 sine x. That's going to be 1 minus 2 cos x. Set that equal to 0 and solve for x. We do need a finite interval here to get a finite number of answers with cosine and trig functions like this. So that's good. I made it a little tricky by making the interval be not 0 to 2 pi, but negative pi over 2 to 3 pi over 2. That equation is equivalent to cosine of x equaling 1/2. Now maybe you just memorize what x values give you 1/2. But if you're afraid you're going to forget, you can always go back to the unit circle definition of cosine and sine. And if you imagine x to be an angle, which you can in this picture, the cosine of x will be the first coordinate of the point on the unit circle when the angle is x, where this ray intersects the circle. That angle there would be x. And actually, if this is the unit circle, that's also the length of this arc. That length is also arc when the angle is measured in radians. That's why radians is so special. Oops, this got messed up. Yikes. Sorry about that. I'm still not quite used to using these kinds of boards very well. Afterward, cosine of x equals 1/2. Again, the cosine is the first coordinate of the point. So we're after an angle there where the first coordinate is 1/2 here and down here. The negative of x would be the angle there. And based on memorized values, cosine of 0 is 1. That's the first coordinate at this point. And then you go down as the angle moves up towards 0. You would go 1, then square root of 3 over 2, then square root of 2 over 2 at 45 degrees. Then at 60 degrees, or pi over 3 radians, the value would be 1/2. So x is going to be pi over 3 or minus pi over 3 in this interval right there. plus or minus pi over 3 of the two values of x in this interval where the cosine of x equals 1/2. If the interval was something stranger, like 3 pi over 2 to 7 pi over 2, then you have to imagine going around the circle completely to get you to an x in the interval that I just mentioned. So those are the critical points. So now we need to evaluate the function value at the critical points and at the endpoints. Now this is a bit of a pain, you might say, without a calculator. And it's going to feel a little bit uncertain as far as approximations go. You kind of got to just do your best. It's something you technically should be able to do. So we're plugging into the original function, not the derivative. And again, I'm not using the first or second derivative test here. I could use maybe quickly the second derivative test to see where I have a local max or a min, but it's fine to just plug into the function x minus 2 times sine x back into the original function. Negative pi over 3, the sine of that is going to be square root of 3 over 2. No, negative square root of 3 over 2. The sine is the second coordinate of the stopping point. That point is close to negative 1 at the second coordinate. Negative square root of 3 over 2 is what this is. Times negative 2 will be positive square root of 3. This is going to simplify to positive square root of 3 minus pi over 3. It's about 1.7 minus 1.05 or so. That would be about, very roughly, about 0.65 or so. That's very rough. We're trying to do it without a calculator, okay? F of positive pi over 3 is actually going to be the opposite of that one we just found. Pi over 3 minus 2 times sine of pi over 3. This is going to be, this was a negative here. Can't quite see the negative sign so well anymore. It's not working. Now that's a positive square root of 3 over 2. The 2's cancel. You get pi over 3 minus square root of 3, roughly negative 0.65 or so. Again, I'm doing that without a calculator, so it could be closer to negative 0.7 or negative 0.6, I'm not quite sure. Probably a little closer to negative 0.7. Okay, but whatever. What about the endpoints? Let's do those up here. Maybe I'll change color. F of negative pi over 2, plugging back into the original function, gives me negative pi over 2 minus 2 sine of negative pi over 2. Sine of that, negative 90 degrees, is negative 1. This becomes 2 minus pi over 2. 2 minus about 1.57, that's about 0.43. And finally, f of 3 pi over 2, I think that's going to be the high value here. That's 3 pi over 2 minus 2 times sine of 3 pi over 2, which is also negative 1 because it's the same angle. 3 pi over 2 plus 2, that's definitely the biggest, whatever it is. Maybe in the ballpark of 6.7 or so. Okay? So as far as the absolute maximum, the value of x where that occurs is x equals 3 pi over 2. And the absolute minimum, that's the smallest value, negative 0.65, that's going to occur at pi over 3. That's where the absolute min occurs. Okay? So those would be the answers to 1 and 2. Absolute max occurring at 3 pi, x equals 3 pi over 2. Absolute min would occur at x equals pi over 3. What would the graph of this look like? It's, see, at negative pi over 2, it's down at 0.43. Then it goes up to 0.65 when x is negative pi over 3. Back down to negative 0.65 when x is positive pi over 3. And then back way up to a high value, 6.7 or something, when x is 3 pi over 2. It looks something like this, and you can check that with your calculator. So there's where the global max is, and here's where the global min is. The global min does occur at a critical point, the global max does not. On to part B. see, these definitely take a long time. You really need to practice these well to be able to do them pretty quickly. I'm making these maybe a little extra tricky, you might say, with the arithmetic. But the idea is certainly something you should be able to handle. Part B, for what values of x is the graph concave up? Justify the answer. Again, the derivative was 1 minus 2 cos x. Where does that change from increasing to decreasing, or vice versa? Or where is it concave out? Excuse me, I'm not after inflection points. Where is the derivative increasing? That would be where the second derivative is positive. The second derivative is going to be 0 plus 2 sine x. And on this interval that we're concerned about here, that's positive, again, thinking about the unit circle, between 0 and pi. Yeah, 0 and pi. This is positive. The sign is the second coordinate on the unit circle when x is between 0 and pi. And you could actually say the graph is fully concave up on the closed interval. That's, again, not a big deal. Even though the second derivative is 0 at the endpoints, it still would be concave up on the intervals there. You could write these things with interval notation as well. And again, it doesn't matter whether you use an open interval or a closed interval. Part C, find the average value. To find the average value of a function, you need to do 1 over the length of the interval, b minus a, times the integral of the function. A is negative pi over 2, b is 3 pi over 2, b minus a here is 3 pi over 2 minus negative pi over 2, which would be 4 pi over 2 or 2 pi. We do end up dividing by 2 pi to find the average value. 1 over 2 pi. The integral is not from 0 to 2 pi, though it's over this interval here. It's going to be a bit tricky still. The calculations turn out a little better than you might imagine here, but still a little bit tricky. We're integrating the original function, x minus 2 sine x. Here I need the fundamental theorem of calculus to actually evaluate the integral by finding an antiderivative of that function there. Antiderivative of x is 1/2 x squared. Antiderivative of minus 2 sine x is plus 2 cos x. Evaluating this, x goes from negative pi over 2 to 3 pi over 2. Yikes. Well, we are saved by one thing here. When you plug in either negative pi over 2 or positive 3 pi over 2, an angle pointing straight down into the cosine function, you get 0. So the only non-zero things come from plugging into there. That's nice. May not always happen, so you got to be wary. So I got to do 1/2 times 3 pi over 2 quantity squared. That's going to be 1/2 times 9 pi squared over 4. Great, square that. Subtract 1/2 times negative pi over 2 squared. The negative sign will go away when you square. You get a pi squared over 4. So it looks like we have 9 pi squared over 8 minus pi squared over 8. That'll be 8 pi squared over 8, or just pi squared. The 8's cancel. One of the pi's cancels. The final answer is pi over 2, which is about 1.57. Geometrically, the area of a rectangle whose base goes from negative pi over 2 to positive 3 pi over 2, and whose height is pi over 2, the area of that is the same as the area of the integral of the original function. The original function does go negative, so you'd be taking areas under the graph when it's below the above the axis, subtracting areas above the graph when it goes below the axis, and get the same area. So that's the average value. All right, on to number 3. What's my pace here? I guess it's taken me a half hour to do 2 problems. So hopefully I can do it in an hour and a half. I think a couple of the last few problems are a little shorter. All right, so what we have here is a family of functions with 2 parameters. A and B are constants. They are parameters. We need to answer these questions, and our answers will depend on A and B. Okay? You do everything pretending they're constants. What's most interesting to me, though, is what happens then after the end. How does the graph change? How do your answers change as A and B change? I'm not going to get into that because it's not required, but that's something interesting to think about. All right, so here again is our function. It's going to be beneficial to write b over x as b times x to the negative 1 power for the purposes of taking the derivative, because then we will not have to use the quotient rule. Part A says to find in terms of A and B the intervals on which f is increasing. Where is f prime positive? So we need the derivative. The algebra is going to be pretty nasty in this one, but you can do it if you're careful. There's the derivative, right? Bring down the 2ax to the first. Bring down this minus 1, minus bx, subtract 1 from that exponent and get negative 2. We're interested in where is this equal to 0. We're also interested in where it's undefined. It's undefined at x equals 0, just like the original function is. Undefined at x equals 0. Those are going to be the spots where the derivative could change sign. Let's find where where this derivative is equal to 0. Let's set this equal to 0 and solve for x. Probably best to add b over x squared to both sides. And the goal is to solve for x, so I would want to isolate x on one side by itself and everything else on the other side. So, for example, I'd want to multiply both sides of this by x squared to cancel the x squared on the right, giving me an x cubed on the left. And I'd want to divide both sides by 2a. So x cubed is going to be b over 2a. Take the cube root of that. X is going to be the cube root of this, which I think it's going to be best to leave that cube root in terms of everything to a fractional power, a 1/3 power. B to the 1/3 over 2 to the 1/3 times a to the 1/3. There's your critical point, and that makes the derivative equal to 0. And again, there's really, in a sense, another one at x equals 0. It's not even defined there. Those are the 2 spots where the derivative could change sign. 0 and that number there, b to the 1/3 over 2 to the 1/3 times a to the 1/3. Usually when you make a number line like this and you're thinking about where does the derivative change sign, usually you have particular numbers, like that might be 5 or something, and you can plug in numbers in these 3 intervals into the derivative and see whether you get a positive or a negative quantity. Here, because that's a symbolic expression, it's unclear, especially over here, what to plug in. Over here it might be a little easier. I can just plug in any negative number that I want into the derivative. You can also just think about it. Plug in a negative number there. A and B are positive. Keep that in mind. You're going to get a negative minus a positive. Because I square even a negative number, I get a positive. Negative minus positive is negative. F prime is negative over here. Let's go over here. What if x is really big? Again, I don't know what that number is. It could be a large number. If b is large and a is small, that would be a large number. But just don't worry about it. Just imagine plugging in some humongous number, not worrying about the exact value of this thing. If x is large enough positively, this is going to be positive minus a small positive number. A large positive number minus a small positive number is positive if x is large enough. It doesn't matter what a and b are. Though they are positive, that is important to keep track of. So f prime is positive over there. That's going to be part of the answer at least. The only question that's a little trickier is what happens between these 2 points. And again, you don't know what this number is. You don't even know how close to 0 it is. It could be really close to 0, but just in your imaginations, imagine something plugging in something for x even closer to 0. Really, really, really tiny. What would happen? You get a small, tiny positive number minus a large positive number. right? Because if x is really tiny, x squared is going to be even tinier. It's really, really close to 0. B over a really, really tiny number is going to be very big. Small positive minus large positive is negative. So the answer to part A is the interval from this point onward to the right, which you could write with interval notation. And again, it really doesn't matter whether you use a square bracket or a curved brace here. The other material is the most important part of the problem. Technically, you can say it's going to be true on the closed interval that the function is going to be increasing, where we are including the left endpoint. But it goes on forever. I put an infinity over there. Here, we're thinking of infinity as not a number, so we would want to put a curved brace there, a parenthesis. That would be the answer to part A. By the way, before I do part B, I would encourage you to think about what the graph of this function looks like, maybe even reasoning without calculus. I'm about to draw it here, but you should be able to reason this out as well. For example, thinking about this function, when x is a small positive number, that's a small positive plus a large positive. We can get a large positive output. And I do know the function is decreasing when x is close to 0, so the graph's got to be coming down. I guess I'm using calculus there. But again, this function becomes large and positive when x is a large positive number. I get a large thing there plus a small positive thing there. It's still going to be large and positive. The graph has to come back up eventually. This would be the location of b to the 1/3 over 2 to the 1/3 times a to the 1/3 right there. When x is negative, yeah, f prime is negative. The graph goes down. It's got a vertical asymptote here. It's got to look something like this. There's probably going to be a point of inflection somewhere in here where the graph changes concavity, concave up to concave down. How do I know it's concave up over there? Because when x is large and negative, this is going to be the dominant term, and it's going to look like a quadratic when x is large and negative. That's what you should keep in mind now as we continue working through. Because now if we try to do part B, we're looking for local max and min points. It looks like there's only one point where there's a local max or min right there. At a critical point, it's just a local min. They don't ask for the reasoning for why it would be a local min. If you want to give reasons, we could do that. Maybe I'll say that verbally. The first or second derivative test can be used. This is not over a closed interval, so we'd want to think about the first or second derivative test. And you'd want to plug the critical point into the original function to find the coordinates, the y coordinate. We already know the x coordinate. What about the y coordinate? It's a bit of a pain, perhaps trickier than you would get on your actual exam. To plug that thing into this function, this is where it's best to leave it in terms of exponents. We have a times this thing squared, see, a times x squared. That's going to be a b to the 2/3 over 2 to the 2/3, a to the 2/3. And then I need to add b times x to the -1, which means I need to flip this fraction. B times the reciprocal of that fraction is 2 to the positive 1/3, a to the positive 1/3 divided by b to the positive 1/3. Technically, that is the second coordinate. And it doesn't say to simplify it, but let's go ahead and simplify it anyway just to get some practice with it. We do get some cancellation. A divided by a to the 2/3 is a to the first divided by a to the 2/3. You'd subtract the exponents. 1 minus 2/3 would be positive 1/3. You're going to have a to the positive 1/3 on top. You already have a b to the positive 2/3 over 2 to the 2/3. And with the second expression right here, b to the first power divided by b to the 1/3, 1 minus 1/3 is 2/3. I'm still going to get a b to the 2/3 on top. And I still have an a to the 1/3. But now I also have a 2 to the 1/3 on the top. You can combine these things by getting a common denominator of 2 to the 2/3. So I'd want to multiply this thing by 2 to the 2/3 divided by 2 to the 2/3, 1, a disguised form of 1. So it doesn't change its value. So then I can combine the fractions into one fraction. A to the 1/3, b to the 2/3. Remember what I'm doing here, plus I'm multiplying this by 2 to the 2/3 and dividing by 2 to the 2/3. 2 to the 1/3 times 2 to the 2/3 is 2. And again, I'm dividing by 2 to the 2/3. And that simplifies pretty nicely to 3 times a to the 1/3 b to the 2/3 divided by 2 to the 2/3. That would be the second coordinate. Okay, so I'm not going to actually write the coordinates. The answers would be, this would be your first coordinate of your local min, and you could say it's a local min. This would be your second coordinate. If you really wanted to confirm that it was a local min, you'd use the number line to show, as we saw, the derivative changes sign from negative to positive as you pass through that point. The first derivative test would imply it's a local min. You could also use the second derivative test. We could take the second derivative and plug in the critical point and see that we get a positive second derivative because the graph's concave up there, implying it's a local min. And in fact, in part C, I will need the second derivative to find where the function is concave up. You can see from the picture, it looks like it's concave up certainly when x is positive, but also perhaps when x is less than some point here, where the inflection point is. Let's see, I forgot the first derivative, I erased it. The first derivative was 2ax minus bx to the negative 2. So the second derivative is going to be 2a plus 2b x to the negative 3. 2a plus 2b over x cubed. Certainly that's positive when x is positive, because a and b are positive. Yes, the graph is concave up when x is positive. And there you would not want to include the left endpoint because that's where the function's undefined. Is it positive anywhere else? Well, where does the second derivative equal 0? It does equal 0 when x is negative. You've got to realize x could be negative here. That equation is equivalent to 2b over x cubed equaling negative 2a. Flip the fractions. Multiply both sides by 2b. That's going to be equivalent to x cubed equals, careful, negative b over a. Okay, make sure you take the time to check that. I just did it in my head. I guess you could just divide both sides by negative 2a right to start at the start and multiply both sides by x cubed. The 2's cancel. So the x coordinate where you have a possible inflection point, where the second derivative changes sign, would be the cube root of this thing, cube root of negative b over a, which is a negative real number. You can bring the negative sign out if you like. You can also use exponents if you prefer. We're not asked for the y coordinate here. That's good. You can write negative b over a to the 1/3, or if you prefer, negative b to the 1/3 over a to the 1/3. Lots of different ways you could write this. That's your possible inflection point. It's a possible place where f double prime changes sign. You can make a number line and think about this. What about the sign of f double prime? And yeah, if you imagine plugging in a very large negative number into f double prime, you will get a negative quantity because you'll have a positive, you'll get a positive quantity. You have a positive plus a very small negative number is positive. F double prime is positive over here. It's also positive over here. In here, it would be negative. If you plug in a small negative number, this becomes a large negative number, far away from 0. Positive plus large negative is negative. So the answers are the interval from minus infinity to negative b to the 1/3 over a to the 1/3, and yeah, you can include the right endpoint there, but 0 to infinity, do not include the left endpoint there because it's undefined at 0. And again, you probably would not be marked wrong if you just don't worry about whether you should make this a closed interval on the right side or not. Either way is okay. X coordinates of any inflection points. We're really doing parts D and C at the same time. We already have the answer. There's your X coordinate of an inflection point. Right there. That's the X coordinate. Okay? Very, very tricky algebra. If you have a problem like this, it probably will not be quite as tricky. Though I can't guarantee. But it's good to do practice problems that are tricky, because then you see where your weaknesses are. All right, let R be the region in the first quadrant enclosed by a graph, a function, and a vertical line here for an arbitrary positive n. Let's just quickly draw a picture up here. First quadrant means we're over here. The graph of an exponential decay is going to look about like that. That'll be 3 right there. Vertical line, x equals n. This is the region R right there. It's really a region that depends on n. We could call it a function of n if we would like to. Part A, find the area of R in terms of n. Area under a graph, that's just the integral of the function. Don't worry about the fact that n is not specified. It's not a big deal. You want to get the answer in terms of n. We have another parameter, so to speak. Use the fundamental theorem of calculus, find an antiderivative of this, which you should be able to do just by guessing. Technically, you could also use substitution. U equals negative x, and d would be negative dx if you did that. Though if you wanted to keep the u, you'd have to change the limits of integration then to being 0 to negative n in that case. You should get the same answer in the end either way. If you want to be extra careful, do that kind of thing. E to the 0 is 1. This simplifies to 3 minus 3 e to the negative n. You're not asked what happens to this expression as n goes to infinity. But technically speaking, you should be able to find that. Because as n goes to infinity, plus infinity, e to the negative n is going to go to 0. So we're not asked, this is the final answer, we're not asked to take the limit of this as n goes to infinity, but if we were asked, the answer would be 3 minus 0 or 3, which is actually a pretty important thing. What we're really doing in there and taking a limit is doing an improper integral, where the upper limit is infinity. And we're essentially saying that the area under this graph where it goes on forever is finite and equals 3. That actually has some important applications, for example, to probability. You can create what are called probability density functions based on that, although you would not use this particular function. For that, you'd want to use a 1 there instead of a 3 to get a probability density function. The circle thing in the box there, that is the answer to part A, though. In parts B and C, now we need to think three-dimensionally. We're after some volumes in B and C. In B, we're not going to actually integrate to find the volume, though it's simple enough that you should be able to if you were asked to do that. We're just going to set it up, set up the integral. In part C, we will actually find the volume. Okay, so you should be flexible enough to deal with either kind of question. It's not common for both of these to be asked in the same question, but I wanted to do it. All right, so let's focus on part B. Now I'm picking something particular for n in part B. We've got R being the base of a solid, a three-dimensional solid. And we've got something specific about what are called cross-sections perpendicular to the x-axis. They are semicircles. What does that mean? I'm going to draw a picture. And as I draw this picture, you need to think three-dimensionally here. Imagine this with perspective, like this axis is kind of coming out of the screen towards you. This will be the x-axis here. This is the y-axis with perspective. The xy plane, so to speak, is going to go into the screen. And this is a third axis, which is often labeled with the letter Z or Z if you prefer. And we're looking at that same region there in the xy plane up to n equals 4. And we're saying create a solid whose base is this region here, this two-dimensional region, and whose cross-sections perpendicular to the x-axis are semicircles. What that means is, if you take a knife, pretend my hand is a knife, and slice it, the solid, perpendicular to the x-axis, the slices will look like semicircles. Small semicircles over here, large semicircles over here, intermediate semicircles in between. Some sort of partial horn is what this looks like. We want to set up an integral that gives you the volume of that object. Okay? Let's imagine looking at a particular cross-section. What does it look like? It looks like a semicircle. I want to find the area of that semicircle in terms of x. Here I'm using x as a label for the axis, but I can also imagine x is a number on the axis between 0 and 4. Doesn't matter. Either way to think of it is okay. For some particular x, the diameter of this semicircle right here, this length right there, is going to be the same as, in this picture, if x is right here, it's going to be the same as this length right there. In other words, it's the function output, which is positive. That's going to be the diameter. The radius of this semicircle, which we're going to need for its area, also depends on x, and it's half of the original function. If we call the original function f of x, that radius there is 1/2 f of x. The area of this cross-section, call it a of x, it does depend on x as well. It's, the area of a circle is pi r squared. So the area of a semicircle is half that. 1/2 pi r squared. R of x quantity squared, which means I need to square f of x, or 1/2 f of x, excuse me. 1/2 squared is 1/4. 1/4 times 1/2 is 1/8. I get 1/8 pi times f of x squared, which can be simplified because of the formula for f. Let's go ahead and do that. Plug in that formula into there. I got to square 3 and I got to square e to the negative x. Square 3 gives me 9. I can bring the 9 out in front. 9 pi over 8. Square e to the negative x, and I'll get e to the negative 2x. And so that's how the area of the cross-section depends on x. And it does get smaller as x gets bigger. The volume is the integral of that cross-sectional area function from 0 to 4. Why? Well, intuitively, the total volume can be found by adding up little volumes. And you can imagine the integral is adding, if you like. And I'm not being very precise when I write that. I'm not even bothering to write limits of integration. Just think of the integral sign as being adding. And think of these dv's as being little volumes. What little volumes? The volumes of really super thin slices of bread, so to speak. If you imagine this as being a loaf of bread. At some value of x, you make a really thin slice. You make 2 cuts, essentially, that are super close together. Infinitesimally close, you might even say. The volume of such a slice is going to be its cross-sectional area times its width, which is dx. But then you'd want to go over the interval of integration for x, which is 0 to 4. So the final answer is going to be the integral from 0 to 4 of the area function, this thing 9 pi over 8 times e to the negative 2x, which technically you could do, okay? But I'm going to do an actual integral in part C. So that would be the volume of this object, okay? As an integral that we don't actually integrate. Again, I'm being hand-wavy here with these equations. Okay, this is not precise math. I'm thinking intuitively as the total volume is the sum, the integral of the little tiny volumes. But what are those little tiny volumes? They're the areas of these thin slices of bread whose cross-sections of these things have area depending on x equal to this. That is the function we end up integrating. You can also just remember that. You don't have to rethink about that derivation. Part C is also a volume problem. But now it's the volume of a find the volume of a solid generated when r is rotated about the x-axis. That's kind of a weird thing to do if you've never imagined doing it before. So it changes this picture here. I still have the same region R as before, although now I'm back to using an arbitrary n here instead of 4. I'm going to rotate that thing around the x-axis to get a solid that's going to be bigger than the previous solid. And this will look more like a full horn. Something about like that. As far as finding that volume, the principle is the same as the other one. You still imagine slicing it with a knife, so to speak, perpendicular to the x-axis, and figuring out what the cross-section looks like. In this case, it's going to be a circle, or a disk if you prefer, which is the inside of the circle, of a certain radius. But now, careful, the radius is no longer half of the function, it is the function. That radius right there, that distance, is the full height of this function. Tricky, okay? The area is pi r squared, but the radius is the function itself. This solid goes around the x-axis. This is the radius here, which is the full height of the function. That's the same as pi times f of x squared. Going back to the function again, 3e to the negative x, we're going to get 9 pi e to the negative 2x. And that function we want to integrate from 0 to n to get how the volume of this thing depends on n. We actually want to do the integral. From 0 to n. And we'll do part C once we're finished because we want to figure out what happens to the volume as n goes to infinity there. Once again, to do this integral, you can do a substitution. But I hope you've got enough practice with this that you can just see the answer would be negative 9/2 pi e to the negative 2x for your antiderivative. Evaluate from 0 to n. I always double check by differentiating. Negative 9/2 pi e to the negative 2n minus negative 9/2 pi e to the 0. This is going to be 9 pi over 2 minus 9 pi over 2 e to the negative n. There's the answer to part C. That is a negative n there. Negative 2n, excuse me, sorry. That's the answer to part C. For part D, let n go to infinity. E to the negative 2n goes to 0 as n goes to infinity. This goes to 9 pi over 2 as n goes to infinity. So the horn picture, if it went infinitely far, actually has a finite volume, which is pretty amazing if you think about it. Such a finite volume doesn't always guarantee a finite surface area, though. It's kind of a strange thing, though I doubt that happens with this example. All right, on to problem number 5. I think I need another drink of water here. yikes. This one doesn't look so easy. I will tell you, it's easier than it looks when you know your concepts well. Got a function of x. We see an expression involving x in the upper limit of an integral. When you see that, big alarm bells should go off in your mind. I need the second fundamental theorem of calculus here. But because it's not just an x, it's the square root of x, I also need the chain rule. If you want to be extra careful about it, which you probably should be, you might want to define a function g of x, or capital G of x, whatever, to be the integral from 2 to x, not 2 to square root of x, but 3t minus 2 over t plus 3. And use the fundamental theorem of calculus, the second one, directly on g. And f is going to be a composition of that function with yet another function, the square root function. F of x, think carefully here, is really going to be g of f, g of h of x. Why g of h? Because when you plug in a number in for x, you got to take the square root first before you integrate. So the inner operation, the first operation, is the h, the square root function, and the outer one is the integral, g. And before doing the problem, that's just going to tell us right away that the derivative of f is the derivative of the outside function, plug in the inside function, times the derivative of the inside function. G prime can be found from the second fundamental theorem of calculus to be essentially the integrand function, use an x instead of a t. H prime is going to be the derivative of square root of x, which is 1/2 x to the negative 1/2. 1 over 2 square root of x is what that's going to be. Let's start doing the problem now. A is actually pretty easy because square root of 4 is 2. And so we're really integrating from 2 to 2. That's a 2 there. No area under the graph from 2 to 2, the answer is 0. So A is easy. B is where we need the FTC and the chain rule. I need this fact here. And I ultimately need to plug in 4. Let's write it in terms of x first, so you understand the concept. F prime is, of x, is g prime of h of x. Again, g prime of x, like I said verbally, is the integrand function using x instead of a t. T is just what's called a dummy variable. It doesn't really represent anything. Use a different letter, u, whatever. I want to emphasize the variable for this function is this upper limit. What this function really represents is a total area under this graph from 2 to x. X actually can be less than 2 as well, but don't worry about that. So g prime is this thing, the integrand, that thing right there, with an x in place of a t. That's what the second fundamental theorem of calculus says. I need to plug in h of x into g. I need to plug in the square root function into that. So everywhere you see an x, replace it with the square root of x. And hopefully not make a mistake. Replace the x's with square root of x. But don't forget to multiply by h prime, which, like I said verbally, is 1 over 2 square root of x. That's the answer for the general derivative. It can be simplified. You can multiply the top by 1, multiply the bottom by 2 square root of x. The top will stay the same. The bottom, multiply that by 2 square root of x, I'll get 2x. Multiply this by 2 square root of x, I'll get plus 6 square root of x. Now plug in x equals 4 into that. F prime of 4. Square root of 4 is 2. 3 times 2 is 6. Minus 2 divided by 2 times 4. Plugging 4 is 8. Square root of 4 is 2. 2 times 6 is 12. 8 plus 12. I'm sorry, this Bottom right corner is so bad here. That's 6 minus 2 over 8 plus 12. That's 4 over 20, which is 1/5 for the answer to part B. All right, so f of 4 is 0, f prime of 4 is 1/5. Part C says find an equation for the tangent line to the graph of capital F at the point where x is 4, the point we were just dealing with. C, that's going to be f of 4 plus f prime of 4 times x minus 4. This is the formula for the tangent line equation. That's 0, this is 1/5. So it looks like the answer to part C is y equals 1/5 times x minus 4 is 1/5 x minus 4/5. That is the answer to part C. Finally, part D. That's the answer to part C. On what intervals is f increasing? We are focused on non-negative values of x. Justify, I want to justify by saying I'm looking for where f prime is positive. Find where f prime of x is greater than or equal to 0. Oh, and I erased f prime, didn't I? Actually, I have the answer here. Capital F prime of x. Oh, come on. Capital F prime of x was 3 square root of x minus 2 over 2x plus 6 square root of x. That's right, yeah. Yeah, that looks right. So where is that positive when x is greater than or equal to 0? Actually, it's undefined when x is 0. There's actually a vertical tangent to the original functions graph there. When x is strictly positive, the bottom's positive. So the only thing you have to worry about is the top, the numerator. That's equivalent to 3 square root of x minus 2 being greater than 0, which is equivalent to square root of x being greater than 2/3. Since x is positive, that's equivalent to x itself being greater than 4/9. And you could include the endpoint as part of your interval in which it's increasing. Actually, I mean, the derivative is going to be 0 there, but you could write a greater than or equal to there as far as part of the answer for part D. Okay, I'll also be able to write that with interval notation. Wow, just one more problem now. Again, a conceptual point here with capital F with this problem. It is an area under a graph, and in finding its derivative, you're figuring out the rate of change of that area as x changes. All right, number 6. Differential equation. Okay. First order differential equation, dy dx equals some expression that involves both x and y in this case. You can think of that as a function of 2 variables. Part A, on the axes provided, sketch a slope field for the given differential equation at the 12 points that are indicated. You got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 points there. The method is to plug the xy coordinates of these points into this function of 2 variables, get a number, draw little line segments with slope equal to that number you get. So, for example, at this upper left point here, whose x coordinate is -1 and whose y coordinate is 1, go up to that formula, replace x with -1 to get -2, minus y is minus 1. This is negative 3. I want to draw a line segment with slope of negative 3. Do you have to get this perfect? No, you don't have to get it perfect. It's impossible to get it perfect. You want reasonable, okay? If it's a slope of negative 3, if we imagine doing a rise over a run with a run equal to positive 1, it would have to go down 3 units. There would be a line going through those 2 points, but I don't want to draw it all the way down there. I just want to draw a small little portion of it. Like that. Probably good enough. And now I do it for the other 11 points. Yikes. There are tricks to save you some work. The slope here is negative 3. Think about this as a function of x and y. If you think of y as fixed, it's a linear function of x with slope or rate of change equal to 2. As x increases by 1, as I move to the right, keeping y constant, the output's going to increase by 2 each time. So if the slope here is negative 3, the slope there got to be 2 bigger, negative 1. Yes, you can double check that by plugging in x equals 0, y equals 1. You get 0 minus 1 is negative 1. Slope of negative 1. About like that. Slope equals negative 1. You don't have to label all these slopes, but I'm just doing it for your benefit here. That's f of 0, 1. The slope will increase by 2 again. When we get to this point, it'll have a slope of 1, about like that. Now go to the next line. First point is negative 2, 0, right there. Plug negative 2 in for x and 0 in for y, you'll get negative 4. Now I need to draw a line with a slope of negative 4, which is even harder to draw accurately here. It's got to be a little steeper than that one. Okay, something about like that probably is good enough. Maybe a little steeper. Slope is supposed to be negative 4. Maybe that's too steep. Okay, it's hard to get it perfect. Okay. Once again, as y stays fixed, as I stay along the horizontal line here, and x increases by 1 each time, again, the fact that there's a 2 coefficient there means the slope keeps increasing by 2. The slope of that is negative 4. Slope here would be negative 2. About like that. Slope here would be 0. Make sure the grader can see that you got a 0 slope there. Slope here would be 2. Down here, x is negative 1, y is negative 1. I get negative 2 plus 1. Careful, negative 2 plus 1 when I plug in this point. Right, double check that. Yeah, negative 2 plus 1 is plus negative 1. Slope of negative 1, about like that. Slope increases by 1 here, so I get a slope of positive 1. Here I get a slope of positive 3. Imagining a point up here, that's going to look about like that. Negative 1, negative 2 gives me negative 2 plus 2 is 0. I get a slope of 0 there. X is 0, y is negative 2 gives me plus 2. This one had a plus 2 slope as well. Let me make that a little steeper looking. There we go. Not perfect, but nobody can draw a perfect picture. Make it reasonable. Part B, sketch the solution curve that contains the point negative 1, 1. Negative 1, comma negative 1 right there. How? You have to follow the slope field. What does that mean and why? The differential equation needs to be imagined as saying, it's really important, I'm looking for a function, y is a function of x, whose derivative, whose slope everywhere, sorry that moved, here we go, whose slope everywhere at any point on its graph equals 2 times the first coordinate of the point minus the second coordinate. Say that again. I'm looking for a function that solves this. There's infinitely many actually. Whose derivative at any point, whose slope at any point to the tangent line equals 2 times the first coordinate of the point you're looking at minus the second coordinate of that same point. For this point, -1 with the slope field has a slope of -1 there. A solution curve passing through that point has to have a slope of -1 at that point. This red line has to be a tangent line there. If you sort of imagine it following the other lines and their slopes, it's got to be concave out there. And, well, here's where it gets a little tricky. You also look ahead to part C. There is a straight line solution. There is a linear function that solves the differential equation, and I hope you're inspired to hope that it maybe is a line about like this. And also, solution curves, distinct solution curves cannot cross each other, so this graph has to be asymptotic to that one as t goes to plus infinity. T goes to minus infinity, we just sort of go back this way with it being concave up. It's going to look something like that. That's the answer to part B. Kind of have to, in some of these problems, look ahead a little bit to give you some inspiration sometimes. In this case, there is a straight line solution, and it looks like it's going to be a straight line solution with a slope of 2 and a y-intercept of -2. We could guess that is the answer for part C. If you were feeling uncertain about a guess, how could you do it? Part C here. Find an equation for the straight line solution. There is one through this point. Really, the only thing that's unknown about it is its slope. You could call it m. It goes to the point 1, 0, so you, as a linear function, you would be able to write it like this. Its value at 1 is 0. And so now it's really just a matter of figuring out m. And I'm guessing m is 2 from the picture, because that straight line looks like it has a slope of 2 and a vertical intercept of -2, which would match this. But to confirm it, we should figure out what m is to solve the differential equation. So we need the derivative, which is the left-hand side of the differential equation. And we also need to plug, here's the trickiest part, plug the function there into the right-hand side in place of y. Y is the function. That's the hardest thing for people. So you're looking for a function whose derivative is always 2x minus itself, minus the function. Y is a function of x. That's the hard thing. Is y a point, is a second coordinate of a point, or is it a function? It's both, depending on how you're thinking about it. When you're thinking about the differential equation itself, you're thinking about y as being a function of x. When you're thinking about the slope field, you're thinking of y as being the second coordinate of various points. That's the most confusing thing. What does the right-hand side become when you plug it in? Plug in place of y, plug in the function mx minus m. This simplifies to 2 minus m times x plus m. We want this and this to be equal no matter what x is. Equal for all x. And that's going to happen if and only if m is 2. Right? That's a constant function. That's a linear function. This coefficient goes away if m is 2. This constant equals that constant no matter what m is. But to make this part go away, m has to be 2. Just like we guessed from the picture. So the answer to part C is this function with 2 in place of m. Or should I write it? Green. Y equals 2x minus 2 is the answer to part C. One more part to do. Wow. Let's see. Part D. You need this type of thing to be in a free response portion to be able to do it. Should if C is a constant, any constant, then this function is a solution of the differential equation. Do the same kind of thing we did to solve for m. Plug that function into the left-hand side and the right-hand side of the differential equation. dy dx, for that function right there, is its derivative, which is 2 minus 0 minus, because of the chain rule, c e to the negative x. I'm trying to show the right-hand side, 2x minus y, when I substitute the function for y equals the derivative no matter what c is. The value of c is irrelevant. Plug in the function. And yes, the 2x's cancel. Minus negative 2. Sorry. Gives you plus 2 minus c to the negative x gives you minus c to the negative x. And we have a match. This matches this. They match. So it's a solution. No matter what c is. It's a solution for any c. C doesn't matter. This is called the general solution of the differential equation. It's a solution for any c. You can also solve what are called initial value problems by taking given points and solving for what c would have to be to make sure this function's graph goes through a given point, like -1, -1, or 1, 0. You'd be solving an initial value problem. They didn't tell you how to actually find this function. That would be a subject for a class on differential equations. If you're interested, this is called a linear differential equation. You can either solve it with something called integrating factors or essentially some educated guessing, though the educated guessing does involve some techniques as well. Okay? But again, that's how you check something as a solution. Plug the function into the left-hand side, find its derivative. Plug it into the right-hand side in place of the y. Simplify, see that you get the same thing. You should also check that no other function will solve the differential equation. You could come up with other functions, any function you want. If it cannot be put in this form, it will not be a solution of the differential equation. That's also an interesting and important thing to know as well. Thanks for watching.